All right, so we are solving our chemistry tutorial sheet questions in this video. Okay, so the first one is round off the following numbers as indicated. Okay, so the first one we have 0.9997654. We round it off to three significant figures. Okay, so what are we going to do? So let's write this number. So 0.9997654. So how can we round off this number to three significant figures? Okay, so we have to know the rules of rounding off. Okay, so we are going to draw a line here. Okay, so these here are three significant figures. Okay, and then we are going to round off this value here, 7. So we have to know the rule that we use in order to round off. So if this number, okay, this number here before, the number here after your desired number of significant figures, okay? If it is less than 5, okay, then we don't do anything to the previous number. So if it's less than 5, the number remains the same, okay? So if, for example, I had 5.2, and then I'm rounding off this 2 here. We see that this 2 is less than 5. So this number is just going to remain the way it is. Okay, if I round it off, it should just be 5.0. Okay, and then if, okay, the preceding number before your desired number of significant figures is greater than or equals to 5, then we have to round off. Okay, so by rounding off, it means we add 1 to the previous number. Okay, so we add 1 to the previous number. So for example, if I have 7, okay, 0.7 like that, and then I'm rounding off at this point here. So this 7 here is greater than 5. Okay, so it means we're going to add a 1 to this 0. So when you round off that number, it just become 71. Okay, so these are the rules that we are going to be following. So when I go here, okay, what will happen is that this number here, the 7, it's greater than 5, okay? And we have to round off this next number here. But the next number that we can see there is 9, okay? So if we add 1 to 9, it's going to become what? 10. So I'm going to write 0 there, and then I'm going to put the 1 here. So this one that I've written here, I'm going to add it to the next number here. Okay, if I add it to the next number, this number again becomes a 10. So you just write 0, okay, and then you write your 1 there. Okay, and then we add this 1 to the next number. So if I add 1 to this 9, again, it's 10. So I just write 0, and then I put the 1 there. Okay, and then now this one, we're going to add it to the next number, which is 0. Okay, so here there's a point, remember. So if I add 1 to this 0, it's going to become what? 1 like that. Okay, so this number here that we've written, we've rounded it off to 1. And this one here has how many significant figures? Anyone who can tell us how many significant figures this number that I've written has? How many significant figures? Hello, come on, guys. How many significant figures does this number have? Okay, so this number here has 4 significant figures. Okay, so remember the rules of significant figures. We said the first one is all non-zero numbers are significant. So if a number is not a zero, like 1, 7, 9, okay, 11, 12, as long as it's not 90, we said these are significant. Okay, and then we said we had 3 separate rules that we are going to classify the 3 types of zeros that we have. Okay, so if, for example, I write this number here, 0.05000500. Okay, so in this number that I've written, we have 3 types of zeros. We have 1, the leading zeros. So meaning the zeros before the non-zero digits. Okay, so these 2 zeros here are leading zeros. We said those the leading zeros there, we said they are not significant. Okay, significant. They are not significant. And then from that, we classified the in-between zeros. okay, or the captured zeros. So if you have two zeros that are between two non-digits like that, we say these zeros here are always what? Significant. They're always significant. And then if I have trading zeros there, okay, so trading zeros, I mean the zeros that come after the non-zero digit. So the non-zero digit here is five, and then we have these zeros. So these trading zeros, we said they can only be significant if in this number we have a decimal place, a decimal point, I mean. So we can see that here we have a decimal point. So it means these zeros here will be what? Significant. So those trading zeros are only significant if in the number you have a decimal point like that. So it means if I have 1, 0, 0, 0, okay, in this number here, I only have one significant figure, okay, or one significant number, which is this one here. These trading zeros here will not be significant. Why? Because I cannot see any decimal place in this number, okay? But in this case, these here will be significant because I can see a point there, okay? So if I go back now to my number here, which is 1.000, okay, we see that it is 1.000. So because I have this decimal place here, all these trading zeros here will be significant. So it means this number here has what? Four significant figures. But in our question, they want us to express this number to what? Three significant figures. So we're going to cancel 1 0 there. So we're going to say this number here, okay, when I round it off to three significant figures, it's just going to be 1.00. So this 1.00 means one is significant, and these two zeros are also significant because we have a decimal point there. All right, so I've summarized the rules for significant figures here, if you didn't know them, okay? So any question there? Is there any question there before we can go to the next question? Okay, no question. Let's round off the other number there. Okay, so we are going to use the same rules that I'm just from explaining there. Okay, so the next one now we have 999.99876. So we want to round off this number to two significant figures. Okay, so the two significant figures, it means we have to round off from here. Okay, so we check this number. Is it greater than or is it less than 5 or greater than or equal to 5? We see that this number is greater. So it means we have to add a 1 to this number here. Okay, so if I add a 1 to this number, I'm going to have 10. So I'll write 0 and then a 1 here. So this one, I'll add it to the next number, which is 9. So if I add 1 to this 9, I'm going to get a 10. Okay, and because I don't have any number here in front of this 9, I'm going to write that 10. Okay, and then this place here where we are the 9, I'm just going to put a 0 point. Okay, all these here are going to become zeros. So you're going to write 0, 0, 0, 0, 0 like that. Okay, so we now have to make this number here, okay, to have two significant figures. Okay, so how do we make that number to have two significant figures? We are going to simply express this number in scientific notation. Okay, so what we are going to do is that I'm going to move this point 1, 2, 3 times. Okay, so it's going to come there. So this means it will be 1.000, these first 3 zeros, and then we have these 5 zeros here that I'm also going to write like that. Okay, so remember from the rules that I earlier explained, I said the trading zeros here are considered significant if we have a decimal place here. So if we are to count the number of significant figures in this number, it will be 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, why? Because there's a decimal place there. So what we are going to do here is that since we've moved this decimal place here 1, 2, 3 times, it means we're going to multiply here by 10, okay, and then to the power 3. So if you go to your left there, it means your power should be a positive. If we are going to the left, if you go to the left, your power should be positive. If you go to the right, your power should be negative. So here we moved 3 steps to the left. So it means the power should be positive like that. So now we have to figure out how we can write this number here, okay, just to have two significant figures. Okay, so I'm going to write that number as 1.0. Okay, so this here is two significant figures, and then I'm going to multiply by 10 to the power 3. Okay, so now that number is expressed in two significant figures. All right, so any question, guys? All right, so let's go to the next question then. So next question, we have this question here. They're saying, which one is more uncertain between 15 degrees Celsius and 15.0 degrees Celsius? Okay, so to determine which one is more uncertain, we just look at the two numbers that we've been given. Okay, and the 15.0 degrees Celsius. Okay, so you ask yourself, this 15, the way it has been written here, this 15 here, how many significant figures does it have? Okay, it has two significant figures. Okay, 1, 2. And then this 15.0 degrees, the way it has been written there, how many significant does it have? How many significant figures does it have? It has three significant what? Figures. Okay, so the number that is more uncertain is that number that has a fewer significant figures. Okay, is that number that has a fewer significant figures. So we are going to say the number that is more uncertain here will just be what? The first one there. Okay, because it has two significant figures. So more uncertain will just be the 15 degrees Celsius. So this number here will be more uncertain. Why? Because it has the fewer significant what? Figures. So sometimes they ask this question in this way. They'll ask you which one is more certain. Okay, which one is more certain between whatever numbers that they will give you. Okay, so just look for the number that has more significant figures than the other. That number will be what? Certain. Okay, but in this case, they were asking us which one is more uncertain. So we pick the one with the fewer significant figures. All right, so any questions there, guys? All right, so we go to the next question then, which is here. Okay, so the question reads, they're saying, okay, so they're saying the concentration of calcium in milk sample was recorded as 30, was recorded as 380. I can see a point there, okay, 380 point parts per million. So this ppm means parts per million, okay, of the calcium. So the first question here, they're saying indicate the certain and the uncertain digit in the above measurement. So this above measurement is 380, and then I have like a point there, okay, and then parts per million. Okay, so this one here is it's a very important component of the question. Okay, so don't ignore it. Okay, it's the one that is going to help us find the answer in this case. Okay, so when you are given a number, okay, any number that you are given that was obtained through measurements, okay, it has a certain digit, okay, and it has an uncertain digit, okay. So if you have a number that has a decimal place there, okay, the number just before the decimal place here is what we call as the uncertain digit. So this one here becomes our uncertain digit, okay, because it's just before this decimal place. And then um, these two here will become the certain digits. Okay, so these here are certain. We can say these are certain. Okay, then this here is uncertain. Okay, so this uncertainty comes from the measuring instrument that you are using. Okay, when you go to your labs, you have different measurements. Okay, so all those different measurements have a degree of uncertainty. Okay, so that degree of uncertainty, you're going to find it in the last uh, digit when you're given a measurement that has a point like that. Okay, so the certain digit here will just be 0. We're going to say the certain digit is 0, and then the certain digit, okay, will be the 3 and the 8. All right, so that's how we can answer the first part. And then number 2, we are answering they are saying number 2 here on B, they're saying considering the uncertainty in measurements, okay? Determine the higher reading, the lower reading, and then the uncertainty range. So how do you determine the higher reading or the lower reading? Okay, so you look at your number that you've been given. Okay, you look at your number that you've been given, and then you focus on the uncertainty digit. Okay, so let me rewrite it here. So you focus on the uncertainty digit. So we have 3, 8, 0 point like that. Okay, so we have to focus on this uncertainty digit. So remember your abacus when you are in, I don't know, grade 1 or something. We said on the abacus, we had this line here that represented the ones, okay? We had another line that represented the tens. We had another line that represented the hundreds. And then we had this one that represented the thousand here. So in this number here, okay, this 0 here represents the ones. This is the 10. This is the 100. Okay, no wonder here it's 300. And then this is in the form of the tens. So how are you going to find the higher reading? Okay, you have to find what we call as the uncertainty range. So the uncertainty range, you just go to the place where you have your uncertain digit. So the uncertain digit here is in the place of the ones here. Okay, so it means the uncertainty range, okay, uncertainty, it means uncertainty range there is going to be equals to, okay, the place where you have your uncertain digit, So the place where we have our uncertain digit is this ones here. So it means our uncertainty, not our uncertainty range, what am I saying? The uncertainty, okay, because the uncertainty range, we use another formula to find it. So this one here is just the uncertainty. Okay, so the uncertainty, you are going to find it by saying plus or minus, and then just getting the part where the uncertain digit is. So the uncertain digit is in the ones from this abacus, we can see, right? So we have 0, 8, and then 3. So this uncertain digit is in the ones like that. Okay, so we are going to say the uncertainty is just plus or minus 1. Okay, so if, okay, if your uncertain digit was in the tens here, it means your uncertainty will just be plus minus 10. Okay, if your uncertainty, if your uncertain digit is in the hundreds, okay, it means your uncertainty will be plus or minus what? 100. So that's how it works. Okay, in case you didn't know. Okay, so I've explained here. So this is the uncertainty here. So from the uncertainty, we are going to use it to find the lower reading and the higher reading. Okay, so we are going to say higher reading is just equals to the reading itself plus the uncertainty, which will just be what? 1. Okay, so it means the 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 higher reading there will just be what? 381. Okay, and then the lower reading will be equals to 380 and then minus 1. Okay, so we have used the plus to the higher reading, the minus we use it to the lower reading. So it means here the lower reading will just be what? 379, like that. Okay, and then from there now we can calculate our uncertainty range. Okay, so our uncertainty range will be equals to, okay, our uncertainty range will be equals to the higher reading, okay, the higher reading minus the lower reading, like that. Okay, so we just have to subtract 381 minus 3 70 79. Okay, so here I wrote something else, right? Okay, here it's supposed to be 380 minus 1, which will give us 379, not 97 there. Okay, so I made an error there. Right, so I've corrected it. So it means the uncertainty range will just be 381 minus 379 there. Okay, so uncertainty range will just be equals to, what is 381 minus 379? It's just going to give us 2. Okay, so our uncertainty range will just be 2, like that. All right, so any questions there, guys? Any questions? Right, so if there are no questions, I'll move to the next question. okay, where we have
I have a
this question
question.
here. Oh, okay, you can ask.
Okay, so after finding the higher reading and the lower reading, are we
Mhm.
supposed to do away with the decimal, or we're supposed to add it?
Okay, so even if you add it, if you don't add it, it's still the same. So if, for example, this 181, we put a point there, even this one, we put a point there, right? Okay, it means the difference will just be 2 points like that. Okay, so it's the same, even if you add it or you don't add it.
Okay, sir, thank you.
All right, you're welcome. All right, so now let's look at another question, which is on finding the number of atoms, finding the number of molecules to mass, just like that. Okay, so this question is a very common question. Okay, it's almost asked everywhere. Okay, so we have two types. Okay, two types of ways. Okay, in which we can solve this question. Okay, the first one is where we use the Avogadro's constant. Okay, Avogadro's constant. Okay, so this one here is the most common method. Okay, and then we have another one where we use the atomic mass unit approach. Okay, so I have videos on my YouTube channel where I was explaining the Avogadro's constant, and I was also explaining the atomic mass unit approach. So make sure you watch those two videos. Okay. All right. So here they are specifying that we have to use the atomic mass unity approach in both questions. Okay. So what are the questions now? So the questions are saying calculate the mass of nickel that contains that contains 2.6 multiplied by 10 to the power 19 atoms. Okay. So the good part in chemistry is that you can convert the mass, okay, to number of particles. You can convert the mass to number of particles. So these particles here, okay, one, they can be atoms. The particles can also be molecules. They can also be electrons. And they can also be what? Ions. Okay, so we can convert the mass to the number of particles, and that particles, okay, it can refer to the atoms, to the molecules, to the electrons, and to the ions. Okay, so we can convert mass to all these that I've listed here. All right, so let's first of all look at the first question there. So we are using the atomic mass unit approach. Okay, so if we are using that approach, then we have to know some certain standard formulas that we are going to be using to convert. So they are more like conversion factors. Okay, so the first one is that one atomic mass unit, okay, is equals to 1.661 multiplied by 10 to the power minus 24 grams. Okay, so this here atomic mass unit here, okay, it refers to the mass of an atom on the periodic table. Okay, it refers to the mass of an atom on the periodic table. So if, for example, you go on the periodic table and then you check the mass of oxygen. The mass of oxygen is about 15.99 and then 7 like that. So this mass of the oxygen is measured in the units that we call as atomic mass unit. Or these atomic mass units are the same as what we call as the molar mass. Okay, so the molar mass, we said its units were moles. I mean, its units were grams. Okay, its units were grams per mole. Okay, so on the periodic table, these masses are measured in atomic mass units, or you can say grams per mole. Okay, and then uh, this here is the first relationship that you must know. Okay, so one atomic mass unit is equals to 1.661 times 10 to the power 24 grams. Okay, and then you must also know that one atom, okay, of any element, okay, one atom of any element is equals to the atomic mass of that element. Okay, atomic mass of that element. of that element here. So meaning if I have, for example, one atom, okay, one atom of oxygen. If I have one atom of oxygen, it means its atomic mass, okay, will just be the 15.997 atomic mass units like that. So this is what I mean by this statement here. Okay, so we are going to use these two statements that I've outlined there to find the mass of nickel that has such number of atoms there. Okay, so here we've been given in nickel. Okay, we want to find the mass of nickel that contains these amount of what? Atoms. Okay, so first of all, we are going to say, okay, we go on the periodic table, and then we are going to say that one atom of nickel, okay, one atom of nickel here has the following atomic mass unit. So the atomic mass unit is just the molar mass of that atom on the periodic table. Okay, so when you go on the periodic table, the atomic mass for nickel is 58.6934. Okay, so we are going to say this here is atomic mass unit. So one atom will have this atomic mass unit. What about 2.6 multiplied by 10 to the power 19? How many atomic mass units are they going to have? Okay, so we are going to write here 2.6 multiplied by 10 to the power 19 is equals to X atomic mass units. Okay, so from there we're going to cross multiply. So let us cross multiply. So we cross multiply here. What are we going to have? Okay, we are going to have X is equals to, and then we multiply this number multiplied by the atomic mass unit. Okay, so if I multiply that number, I'm going to get the following. Okay, I'm going to get on my calculator, it's saying 152.60284 multiplied by 10 to the power 19 atomic mass units. Okay, so it means these amounts of atoms of nickel have this much of atomic mass units. Okay, and then once we find the atomic mass unit, we can now go back and use this relationship here on top to find the mass. Okay, so from that relationship, we know that one atomic mass unit is equals to 1.661 multiplied by 10 to the power minus 24 grams. Okay, and then from there, what are we going to do? We are going to say, what about 152.60284 multiplied by 10 to the power minus to the power 19 atomic mass unit? Okay, how much mass are these going to have? Okay, so we are just going to cross multiply. So there we cross multiply, it will be X multiplied by 1. So it will just be X is equals to, and then you multiply this number here, okay, multiplied by this number here. So what are we going to get when we multiply that? Okay, so I'm going to write them here. So 1.661 multiplied by, I'm going to say by 152.60284, and then multiplied by, okay, this one here, the power, a 10 power 19, and then multiplied by this first one here, the 10 to the power 24. So 10 to the power minus 24 there. All right, and then we can simplify that, okay? Or we can patch it on a calculator to find the answer. Okay, so it means our X will just be equals to, let's punch this value here into our calculator. All right, so when I punch that value onto my calculator, I'm getting this as my answer. Okay, I'm getting 2.5347 multiplied by 10 to the power minus 3 grams. All right, so this will be my mass here. So you can round it off to 3 significant figures. Okay, so 2.73 multiplied by 10 to the power minus 3 grams. Okay, all right, so this here will be the mass of nickel, okay, that has those amount of what? Those amount of atoms. All right, so any questions there, guys? Any questions? Right, I'm happy if you're understanding. Okay, if you're not, please ask. All right, so the next one now will be calculating a question that involves molecules. Okay, so molecules, we are going to follow a similar approach. Okay, but on the, it's just going to differ on uh, the number of, I mean, the mass of, the atomic mass of a molecule is going to differ at that point. Okay, so we're still going to use our ratio, which says 1 atomic mass unit is equals to, okay, 1.661 multiplied by 10 to the power minus what? 24 grams. We're still going to use this relationship, okay? But another relationship now that we introduce, because here we're dealing with a molecule. Okay, so let's read the question. The question says calculate the molecules, okay, in 4.78 multiplied by 10 to the power minus 6 grams of what? Ammonia. Okay, so that is ammonia, the NH3 there. All right, so the other relationship that we need to know now is that if I have one molecule, okay, if I have one molecule, that molecule is equals to, okay, the molar mass of the molecule, okay, in atomic mass units. Okay, so meaning that here we have ammonia, right? So the atomic mass units that we are going to write here should be equals to the molar mass of that element, of that compound that you have. Okay, so in this case, we have ammonia. So what is the molar mass of ammonia? We're going to add the molar mass of nitrogen plus 3, the molar mass of what? Uh, hydrogen there. So nitrogen has 4.01 plus, okay, this hydrogen here has 2, I mean it is 3 multiplied by 1.01. Okay, so meaning we're going to have what as our molar mass of this ammonia? Okay, it will be 14.01. Then this will be 3 multiplied by 1 multiplied by 0 multiplied by 1. So that will be plus 3.03. Okay, so when I add this, I'm going to get 17.04. So this will be 17.04 atomic mass unit. Okay, so it means that one molecule of ammonia is equals to 17.04 atomic mass units. So these are the two relationships that we're going to be using here in order to calculate the molecules that will be in that mass there. All right, so always take note of the compound that you've been given there, okay? So the value that you put here is not always the same. It depends on the molecule that you've been given, okay? So you just get the molar mass of that molecule. So I have a video on how to calculate molar masses. Okay, it's there on Drive, it's there on YouTube. If you don't know how to calculate the molar masses, please refer to that video. Okay. All right, so we're going to use these two relationships here to answer this question B here. Okay, so the first thing that we are going to do here is convert this mass that we have, we convert it to what? To atomic mass unit. And then once we have the atomic mass unit, we can convert them to the number of what? Molecules. So that's how we move. So we are going to say that, okay, we're going to say that 1 atomic mass unit is equals to 1.661 multiplied by 10 to the power minus 24 grams. Okay, so what if I have 4.78 multiplied by 10 to the power minus 6 grams? What will be my atomic mass units there? So we simply cross multiply here. Cross multiply, we're going to have 1.66 multiplied by 10 to the power minus 24x is equals to 1 multiplied by this, we're going to get 4.78 multiplied by 10 to the power minus 6. Okay, so we're going to divide both sides by this same value here. Even this side, okay, we're going to divide by 1.66 multiplied by 10 to the power minus 24. All right, so we see that on the left-hand side, this is going to cancel, so we're just remaining with x. So just punch what you can see here onto your calculator. Okay, so when we punch that into my calculator, what am I getting? All right, so I'm getting 2.8778 multiplied by 10 to the power 18. And these here will be what? Atomic mass units, like that. So these are the atomic mass units that I get. And then you come back to this other formula now. So we know that one molecule is equals to 17.04 atomic mass units for this ammonia specifically. Okay. So what about if I have 2.8778 multiplied by 10 to the power 18 atomic mass units? How many molecules am I going to have there? Okay, so that's what we do. So we can actually cross multiply there. Okay, we can cross multiply there. So if we cross multiply, what are we going to have? Okay. All right, so we are going to say, let's cross multiply here. So if we cross multiply here, okay, we are going to have, let's create some space on the other part here. Okay, so if we cross multiply, we're going to have 17.04x is equals to, and then here we have one molecule multiplied by this much. So we are going to have 2.8778 multiplied by 10 to the power 18. So this is what we have there. Okay, so it means now we can divide both sides. We divide both sides by this 17.04. Even this side, we divide by 17.04. So it means here we're going to have x is equals to, so let's divide that number there on the calculator. Okay, so if I put that on my calculator and then I divide, I'm going to have the following as my answer. I'm going to have 1.6885 multiplied by 10 to the power 17, like that. Okay, so we can round off this to three significant figures. Okay, we can round it off to three significant figures. So it means we're going to have 1.69 times 10 to the power 17 molecules. Okay, and these molecules will be for what? Ammonia, like that. Okay, so that's how we can solve question B. So any questions there, guys? Any questions there? All right, so if there are no questions, I'll end here. I just wanted us to revise some few questions. Okay, so if there are no questions, I'll end here. Thank you so much for attending.